cloud. Perfect. I'll share the video with you later. Maybe we wait 1 more minute and then I'll do the introduction and then the floor is yours after that.
Sounds great.
Perfect. Okay. So yeah, let's start. First, hello everyone. Thank you for attending our second machine learning seminar talk. Um, we are very glad to host Professor Zsolt Kira from Georgia Tech. Zsolt is the director of Machine Learning Center at Georgia Tech, and his work lies at the intersection of machine learning and artificial intelligence for sensor processing, perception, and robotics. So his current projects and interests relate to moving beyond the current limitations of supervised learning and to tackle unsupervised, self-supervised, and semi-supervised methods with applications in out-of-distribution detection, model calibration, and learning under imbalanced distribution, as well as continual and lifelong learning machines. Zsolt has grown a portfolio of projects funded by NSF, ONR, DARPA, and IC community, and has over 45 publications in top venues. I personally enjoy reading his work and interacting with him in conferences. I think he's a brilliant professor, and we are very happy to have him today here as our speaker.
Awesome. Thank you very much for the kind introduction. And likewise, I really enjoyed discussions I've had with folks from Vanderbilt. So today I'll be talking about handling distribution shift in visual learning. And I'll kind of describe both the fundamental problems that we've been tackling as well as applications to areas such as continual learning. So just a bit of background about me, as Sohail mentioned. We work at the intersection of machine learning, sensor processing, and robotics. And really, there's 3 buckets of categories of work that we do, ranging from moving beyond supervised learning to do few-shot learning, semi-supervised, self-supervised, continual learning, and so on. And obviously, we want to both drive down the amount of labeled data needed in order to do effective learning, as well as continuously adapt to new environments or new categories and so on. We're also doing about half of my lab in terms of embodied AI. So looking at not just perception, but also its interaction with decision-making. And this includes goal-driven perception, looking at following natural language instructions by a robotic agent, and doing things like mobile manipulation, which are low or long horizon difficult tasks. And I think there's a lot of really interesting intersections between these 2 areas. There's a lot of opportunities to leverage self-supervised, semi-supervised, and continual learning methods where you have embodied agents who get lots of unlabeled data for free and obviously have to encounter continuously changing distributions of tasks. And so we try to, and are increasingly looking at the intersections of these 2. And we also do a little bit more robotics work looking at multimodal fusion and distributed perception. Of course, all work is done by my awesome PhD students, so I'd like to acknowledge them here, and I'll point out specific ones that have done the work that I'll be talking about today. So Junjiao Tian specifically, and collaboration with Samsung and other groups have led to the works that I'll be presenting, including James Smith, who's been doing a lot of the continual learning work. And so here's an outline of my talk. I'll be talking about background and motivation of why we want to deal with distribution shift, one of the key fundamental problems in machine learning. Talk about specific types of distribution shifts, specifically covariate and semantic shifts, and then present our methods, geometric sensitivity decomposition to tackle these and actually decompose classifiers into different components where we can actually analyze the effect of different types of distribution shift on the models themselves. And this includes combinations with tasks such as out-of-distribution detection, which again is a fundamental machine learning problem. And then I'll end with application area looking at semi-supervised continual learning, where we'll actually use out-of-distribution detection to deal with continuously learning of new tasks. And then I'll discuss some future work. So I won't have to probably belabor these points, but neural networks have been awesome. They've been doing well across a range of different modalities and tasks. And really, they are doing well under several limiting assumptions. For example, where the training distribution is similar to the testing distribution. And so when they encounter things that are unknown, they're well known to both do poorly, but also still be confident about it. So they are have incorrect answers, but are also providing very confident incorrect answers. And this is tied to some fundamental assumptions that we've been making throughout in machine learning related to IID assumptions, and specifically that we're sampling from the same underlying distribution, both for the training and testing data. And of course, in reality, when you train on something and try to deploy it, for example, on a self-driving car, you will have to deal with changing distributions of data. It's really hard and probably impossible to get data from all possible distributions that some agent or robot will encounter in the real world. And this includes things like weather conditions. If you're training during spring and encounter winter or snow, lighting conditions, day versus night, as well as new types of objects that you have not learned about. This is actually an image on the right from a cool data set called Fishyscapes, where they insert all sorts of random objects like animals into roads. Again, and these things are not reflected in the training set. And one thing I'd like to argue is that a lot of these types of problems are all related to distribution shift, and that is also related to or ties together all sorts of different problems in machine learning, including continual and semi-supervised learning, federated learning, and so on. And so there's a lot of related concepts. And what's interesting is that these have been studied pretty separately across the communities. This includes out of distribution detection or open set detection, where you're trying to essentially detect whether a particular example is in or out of distribution with respect to the training data that you've seen. And actually, there's some cool survey papers that have recently come out that have shown that really a lot of these, even within open set detection, there's been a lot of implicit assumptions made about the specific types of distribution shift that you might get. For example, noise in your sensors, or things like snow or weather conditions versus new categories, which is more of a semantic shift. And there's another related work for calibration or uncertainty estimation. That is, we want models that reflect their underlying uncertainty that correlates with their empirical performance on particular types of data. And again, those have been studied in a siloed manner, where we don't have unified methods that can do well both, for example, on out of distribution detection and calibration. And then there's also work on imbalanced learning, for example, where you have a distribution shift on the label space. That is, your label distribution during training, which is often long-tailed, is different than the actual label distribution you care about in the underlying metrics themselves. For example, you often care in a uniform kind of distribution over the label space, where yes, pedestrians might not be well reflected in your training data, but you're obviously very, you care a lot about that class and all classes, because they might lead to accidents and other things for self-driving cars. And so again, one of the key things that we wanted to tackle is the fact that these have been studied separately, and they have all made some assumptions just by the underlying data sets that they use about what types of distribution shifts occur. And what we argue is that we really want to start looking at this holistically and try to develop methods that are fundamental and principled and can really view this in a global manner. So I'll start going through some of the concepts that are related to a lot of these issues that I've discussed. Of course, the first one is confidence calibration, which is really important. For example, if we want a self-driving car to predict things like whether pedestrians are in front of it, then we obviously wanted to provide estimates, uncertainty estimates that, with probabilities, and that probability should hopefully reflect some actual uncertainty or the empirical performance of that prediction. That is, if the model is predicting 0.9 probability, hopefully under a large set of those circumstances, the accuracy is about 90%. And of course, this is useful for lots of things, especially once you incorporate planning that uses these uncertainty estimates and so on. And it's also useful for other things like active learning or interpretability, where we might want a model that can say whether it's not confident about something and then maybe ask for help from human users. And so specifically, confidence calibration has been studied separately, again, in a siloed kind of manner, looking at aligning the probability or the confidence of the predictions to the empirical accuracy of the prediction itself. So when you have a neural network model, of course, you get a probability distribution over the labels. And we typically just take an argmax and say there's a, this is a dog with 60% probability. And so what we want this to mathematically mean is that essentially the confidence that is 0.6 matches the empirical performance or accuracy of the model itself. That is, you can take all the situations where the model roughly said 0.6 for a probability, and was it actually 60% of the time roughly correct for those examples. So there's kind of a formal definition that you can have where you're defining miscalibration as the difference between these two, between the accuracy, empirical accuracy, and the confidence of the model. And so our overall goal, of course, is to have models that are not overconfident, which is a known problem. And it's typically more severe for things like outer distribution data. That is, if you show it data that it's seen during training, then it might actually have reasonable confidences. And that's typically the case because it's actually much better at predicting those anyway. When you give it out of distribution examples, the confidences tend to be really overconfident. And so we have several goals here in our work. And really what we want to do is a little bit counterintuitive. We want to actually make the models more sensitive to out of distribution data. That is, despite the fact that we often say we want models that are invariant to changes in the data distributions, if we are to be able to both detect out of distribution data and give better calibrations, better calibrated probabilities, then we posit that we should actually make parts of the model at least sensitive to these distribution shifts such that they affect the corresponding predictions. And typically, this is used as scores where we try to perform out of distribution detection as a binary classification problem. And we have some scoring function based on either the features or the probabilities or the logits that somehow determine in a binary way whether it's in or out of distribution using like a threshold on the score. And again, one of the goals is that the confidences should decrease according to the deteriorating performance. That is the empirical accuracy of the model. And so there's been a lot of works on looking at calibration, of course, and a lot of these works actually look to disentangle types of uncertainty. There's, of course, model uncertainty, which is kind of epistemic uncertainty, and this is reducible as more data is available and can be captured kind of via a posterior over parameters. This is actually well studied, and there's a lot of really good theses and works. And really, this is assessed via something like out of distribution detection or calibration. You could also have what's called aleatoric uncertainty, which is just inherent randomness in the environment. And you can't really reduce this, it's just stochasticity that exists in the environment, but you can capture it via things like data likelihood. And you can assess it via like in distribution error detection. And so you have these two kind of perspectives, and a lot of works have looked at, for example, using Bayesian neural networks to disentangle these types of uncertainty. And there's a lot of issues with these methods. First of all, Bayesian methods, full Bayesian neural network type methods just do not scale well. They're not very scalable in terms of the number of parameters to large models and large data sets. And there's some methods that use some mixture of density estimation or just using the softmax probability distribution and other measures on top of that, such as entropy. And again, these methods tend to be pretty complex. They have a ton of hyperparameters. Sometimes they even require getting access to out of distribution data and so on. And so what we essentially posit is a different perspective, which is that rather than looking at the sources of or types of uncertainty, we should actually look at the sources of uncertainty or what causes uncertainty. And these are often, again, distribution shifts that the model encounters. So there's no need, we posit, to disentangle things like aleatoric and epistemic uncertainty, which you need things like Bayesian neural networks or density models. Rather, what we're going to do is define different types of distribution shift and try to develop methods that somehow disentangle different types of distribution shifts and understand at a mechanistic level how they affect the model and its predictions. And specifically, we can go back to traditional machine learning definitions for different aspects of what can shift in our underlying distributions. You can have covariate shift where the conditional, the y given x is actually the same. That is, you have the same label space, but the underlying input distribution shifts. So this can be things like noise in your sensor data or different weather conditions and things like that, but you're still trying to detect or classify the same objects. You can have concept shift, which looks at the reverse, where your conditional is different because you have a different label space. You're trying to classify or detect new types or different types of objects, but your underlying data distribution is similar. That is, it comes from this similar data set. And this can be something like, the same texture and style of the data. And of course, these two in real world are never completely disentangled. If your classes change, the categories that you're trying to classify change, then of course the underlying data distribution might change as well. But we're talking about kind of the same underlying texture or style kind of input distributions. And then you can have actually prior shift, for example, just the same label space, but different distributions. This is, for example, the long-tailed imbalanced learning problem. We do have work for this, but I won't focus too much on this for this talk, and I'll provide references at the end. So what I want to talk about today is two works, one that actually look at fundamental methods to disentangle how distribution shifts can affect and how can we ameliorate or make the model more sensitive to these distribution shifts such that we can detect them. And then I'll talk about some applications to continual learning and how we can actually use these methods. So this is some recent NERD spotlights that you can check out. And the key kind of, again, problem that we're tackling here is the first one is of calibration. And specifically, again, we want to make the model sensitive to outer distribution data. If the model is fully invariant to various transformations that include things like input distributions, then it has no chance of actually reflecting this in the feature space or in the prediction space such that you can actually detect whether something is out of distribution. And so we came up with a method called geometric sensitivity decomposition, which I'll talk about, to actually disentangle these effects and try to make the model more sensitive. And then again, to make the confidence decrease according to deteriorating performance, which can be measured for calibration, we also disentangle kind of training and have a post-training calibration. Again, all on in-distribution data. We don't assume any access to any out-of-distribution data. And so I'll go through the method, and the method really relies on a geometric interpretation of classifiers. And again, this is not something that we developed. It's something that prior methods have also talked about. And of course, in a deep learning model, you often have a feature extractor, a convolutional neural network, transformer, whatnot, that output some set of features or transformations of the input raw data. And then we often have a linear layer that converts those features into logits, which are often interpreted as scores for each class. And then we often use softmax to retrieve a predictive distribution. And then we can have cross entropy loss, for example, to train this. And again, there's been prior work that looked at this and said, well, we can actually disentangle this into two components. One is a norm component of the features. So that is you're kind of measuring the norm of the features, and another component that relies on the angular kind of component. And so again, this decomposition is just a mathematical one. We can do this, and this has been done in the prior works cited on the bottom. And our observation is that based on this geometric interpretation and disentanglement is that the neural network can really do things that are suboptimal for calibration and out of distribution detection. And specifically, it can really drive the feature norms very high. And by doing this, it really reduces the loss. And what this means is ultimately you'll have very high confidence samples. And this is true for out of distribution data as well. That is, it'll drive the norms of the features really high for everything. And so it'll no longer be sensitive, like I mentioned, to out of distribution data. Similarly, the angle will be driven to be very low. and the cosine of the angle approximately 1. And again, this is a undesirable thing because it makes the angles not sensitive to these things. There's also prior works that also show that these two components have sensitivity to different types of distribution shifts. Specifically, the norm is more sensitive to things like covariate shift, that is the shift in the input distribution, which makes sense. And the angle is more sensitive to semantic or interclass kind of distances. And so we'll leverage that later on as well. And so we came up with a method to solve this. Again, the observation is that the norms tend to be very large in order to minimize training data because we're using empirical risk minimization. And what this means is that the norms tend to be insensitive to outer distribution data. And again, this observation comes from prior works, but also we have validated it. If you look at the paper, we have experiments showing this as well. So our actual method is super simple. What we do is decompose the norm into two components. We'll have an instance dependent component that is, again, kind of the normal features that are back propagated through to optimize them. And then we'll also have an instance independent factor here that is a learnable parameter, but is a simple kind of, doesn't add that many parameters, but gives the neural network flexibility. That is, it can still have feature norms that are very sensitive to different things like outer distribution data. Of course, we're only training on in-distribution data, but you always have, a spectrum of inliers and outliers, and you'll have interclass or intraclass variance and so on. And so this will allow the neural network to have flexibility to learn features whose norms can be very sensitive to whether it is in or out of distribution or close to kind of the means of or the modes of the distributions of the data that it sees. And then it can also have an instance independent one to kind of, if it wants to drive the loss down. And so this is a very simple idea, but this is what we do for the norm. Similarly, for the angle, we have another same idea where we, in this case, it's a minus because, again, it's the reverse where the angles are being driven to be very low and the cosine of the angles close to 1. And so here, again, we add a learnable component here. So the key idea, again, is to provide flexibility for this angle to be sensitive or not to different types of data, depending on whether it's kind of close to the modes of the distribution seen during training or not. And so this is kind of what we do. We have a new kind of logit definition, which essentially just takes the previous disentanglement and adds these two learnable components. And then we can make some assumptions. For example, we can assume that the angle is very small. And again, we have empirical verification of this. And if you have that assumption, you can actually have a derivation that I'm not going to go through in this presentation, but you can look at it in the paper that really just results in a new logit definition that has two learnable simple components. But again, this is through some principal derivation to understand exactly their form. And typically here, alpha is kind of related to the angle. So it's bound here between 0 and 1, whereas beta can just be anything above 0. And so this is essentially what our method is to allow flexibility for the neural network to learn norms and angles that are sensitive to input distributions without sacrificing its ability to drive down the loss function. And then we have, again, the same softmax classifier, of course, after that, using these new logits. And you can do various tricks for this paper, but actually not in all papers that we've published subsequently. You can actually not even have the alpha learnable. You can just regularize it close to 1. And we're really focusing on empirically on improving the sensitivity of the norm to things like covariate shift, that is this changing, adding noise to the data and so on. We also have a calibration procedure on the validation set. Again, this is all on the in-distribution validation. We don't have any other distribution data. And what we do is, again, because alpha and beta kind of our parameters might overfit, when they're learnable, again, we just backpropagate through them. But during the validation after the fact, we can then either, again, regularize alpha to 1, or we cannot, but we can kind of calibrate these two things. And specifically what we do is We just do minimization of the negative log likelihood on the validation set. So this goes from beta to beta prime. And similarly, you can do it from alpha to alpha prime if you want. And is just a post-training calibration procedure that you only do once on the validation set. We also have actually something that we no longer use after this paper, but can get some better empirical performance in some cases, which is mapping the original beta prime by driving it essentially exponentially away from the in distribution data. So the more it kind of moves away from in distribution, we're mapping it more aggressively to be kind of not in distribution. I won't talk too much about that, but essentially the kind of overall method then we have is very simple. It's really the fact that we're disentangling the norm and the angle. We have these two learnable components that allow flexibility for the neural network to learn norms and angles that are sensitive to outer distribution data. We have a post-training procedure where we're calibrating, for example, beta to beta prime, again, just on the validation set. And then we have this exponential mapping as well in this paper. And again, this whole calibration step is only done once. This is just a post-training procedure. And so what we want to, again, we made a lot of claims, both that the neural network drives the norms high and the angles low. We made some claims that adding these learnable parameters through our derivation will give flexibility to the neural network to actually make the norms and angles sensitive to different types of distribution shift. And so, of course, now we can have a bunch of experiments, including some that I won't be able to show in the paper, but that are in the paper in order to validate these. And so, for example, we've validated the fact that this beta, which corresponds to this instance independent factor for the norm, actually does allow the network to learn a smaller norm that's, again, more sensitive to out of distribution data. And the way we do this is we just vary the beta manually. So we don't make it a learnable parameter, we just vary it manually. And we show that indeed the neural network tends to learn high norms. If we have no beta, then it learns really large norms on average. And if we progressively make beta more aggressive, then it can learn feature spaces that have smaller and smaller norms. And again, what this does is the fact that it's not just driving the norms high for everything, it's able to actually distinguish in a more fine-grained way in and out of distribution data. And of course, in practice, we make this learnable and then calibrate it, but this was an ablation kind of experiment to just verify our correlation between this beta factor and the norms of the model. Similarly, we did this for the angle, showing kind of the reverse thing, again, because the angles are driven to be smaller. And so now we can say, okay, is the model better calibrated? And we can do this as is typical under various types of distribution shifts. One of the interesting things is, again, calibration, and as I'll talk about later, out of distribution detection are typically studied kind of in a siloed manner for particular types of distribution shifts. And they don't really make this explicit. It's really just a function of the types of data sets that they use. So here, for example, again, a common data set setting that they use is the in distribution is CIFAR10. That's the training that you do on the model. And the out of distribution is CIFAR10C, which is corrupted by all sorts of different things. This is from an iClear paper that corrupts images in various ways in various severities. And there's several metrics you can actually measure calibration. There's this paper, the iClear paper, again, not our work, came up with this expected calibration error metric, which of course is an error metric, so lower is better. And we can compare it to all sorts of state-of-the-art methods that use all sorts of different types of sophisticated methods, including kind of density estimators and so on. And what we indeed see is that our results are actually state-of-the-art if we apply these kinds of learnable components and disentangle the norm and the angle and provide flexibility through these learnable parameters for the model to be sensitive to these things. And specifically, you can measure, again, corruption, accuracy on the corrupted data. You can measure ECE, the calibration error, and so on. And we have two kind of classes of methods: single pass methods, that is non-ensembles, or things that don't use Monte Carlo method like Monte Carlo dropout. And there, again, we're state of the art. If we do that, what's interesting is we can actually combine our method with ensembles and again, beat all the ensemble-based methods. What's interesting is actually in some cases, our single pass method is slightly better or actually comparable to deep ensemble, which is actually usually a really strong baseline. Obviously, they use multiple models and things like that, so they have downsides, but ensembling is actually a really effective method for calibration. So actually, the fact that we can beat it with a single pass method is actually really impressive. And so now there's another question. Well, calibration, again, we claim is related to things like outer distribution detection. Again, typically most people do not study them combined, but we posit that we should have models that can tackle both. And so what we can look at is the outer distribution detection problem, where you have essentially a binary classifier. Typically, you have some scoring function that can then be thresholded to say, is it outer distribution or in distribution? So it's a binary classification problem. And again, the key kind of goal is to drive apart in and outer distribution detection or distribution data using the scoring function. And so we want to also do outer distribution detection, not just on one particular thing. Again, in the OOD community, most people do concept shift, that is, they vary the classes. But actually, we think, again, we should do outer distribution detection on both kind of covariate shift as well as concept shift. And so in order to further improve or come up with scores for outer distribution detection using our disentangled method, we actually derive different scoring functions. And the way we do this is super simple. We have a KL divergence between the uniform distribution and our predictive distribution. And so, of course, a large KL divergence means we have a smaller uncertainty because we're further away from the uniform distribution. And a small KL has large uncertainty. And we actually have in some works, we have this is in the distribution shift workshop paper for NeurIPS, but is also under submission or under review. We can actually derive a bound. So we actually care about this KL divergence term, but we want to actually, again, disentangle this into norms and angles such that we can disentangle and understand in a more fine-grained way how distribution shifts, covariate shift and concept should affect it. And so we can actually prove that the scale divergence term is actually bounded by a scoring function that looks like this, which is kind of familiar. It actually is a scoring function that is a combination or a multiplication of two scoring functions. One is just literally the feature norm, and the other looks like this and is a function of, again, the angular distances. And so we call one G, which again, this is our covariate shift, because we told you that norms tend to be sensitive to covariate shift. That is, if we have noise in the data. And then this is our concept shift score. And again, our claim is that we can use these scores to, in a thresholded way, determine whether something is in or out of distribution detection. And one thing you can now notice is why we did the previous geometric disentanglement, where we added that learnable component, because we claim that we make the norm more sensitive to outer distribution data. And so, of course, if it's more sensitive, then the scoring function will be more effective at discriminating between in and out of distribution. And so this leads to a scoring function. And again, we can combine it with our prior method that I just showed you, which is the GSD, geometric sensitivity decomposition method. And so this is what it looks like. So now we have actually a unified method that essentially applies all of these concepts. It has the geometric sensitivity decomposition to make, it forces the neural network to learn feature norms that are sensitive to outer distribution detection. We use that as a scoring function. And we also use the angular terms, as I showed before, as a scoring function. We can also do separately calibration. And one thing to note is these don't affect each other. Calibration only affects the beta and the alpha, and actually there's no back propagation because it happens during validation sets. So it doesn't actually affect out of distribution detection. But what's cool is we can do both now. We can do both out of distribution detection, we can do calibration, and we can do this without losing accuracy. I should mention that there's a lot of out of distribution detection methods that work well at the scoring function of is it in or out of distribution, but they actually at the underlying task that is predicting the class labels does more poorly. It kind of reduces the performance. In our case, our method can do all three. It can do calibration, it can do out of distribution detection, and it can do inference, all in state-of-the-art ways. And so now I'll go through pretty quickly through a bunch of tables that show you that indeed this is the case. We can do really well. And specifically, we can show, in this case, we're doing the out of distribution detection. So again, a binary classification problem. Typically, we score it using the area under the receiver operating curve. So the AUROC is the metric. And here the in distribution data is CIFAR 10, and the out of distribution data is actually, again, CIFAR 10 with various types of corruptions. And we can show the effectiveness of the different scores that we have. Again, we argued or claimed that the norm is going to be more sensitive to covariate shift, the angle more sensitive to concept shift. So in this case, we should expect that the scoring function, that the covariate scoring function should do better. And indeed, that's what we see. Here we compare vanilla, our beta and alpha methods where we just learn both, or our alpha where we only learn alpha. And again, you can have different variants of learning different parts of the decomposition. That's another nice thing. And again, here, what you can see is if you compare covariate score shift, or covariate score performance, it's better than the semantic score performance. And the joint score is kind of some combination, so it does pretty well overall. But what's cool is you can actually, one thing is that's nice to have like state-of-the-art results. It's also, I think, really a good point is to have, which is you can actually, again, understand different things. So we have a follow-on paper on this where we look at different types of distribution shifts that people study in the literature and say, well, which one is harder? Why is it harder? How does it actually affect, for example, these scoring functions and so on? Because we disentangle them, we again increase our both performance in terms of state-of-the-art results, but we also increase our ability to understand what's going on fundamentally. And we can, for example, analyze whether these data sets are good data sets to measure calibration and out of distribution detection, whether we should maybe add other types of distribution shifts and so on. And so again, now we can look at out of distribution detection on semantic shifts. So again, this is new classes. If you have in distribution here, for example, is CIFAR 100, and then out of distribution is other types of data sets, CIFAR 10 or SVHN, or the in distribution can be CIFAR 10 and the out of distribution is CIFAR 100 SVHN. And again, across the board, we get really good out of distribution performance. And we don't show that here. These are AUROCs. So again, this is measuring how well do we do at out of distribution detection. What we don't show here is that we also don't sacrifice performance on the actual classification task, which some prior methods actually do. And then again, we can show calibration on both types of shift. And I showed covariate shift. Now we can show also semantic shift. And I won't belabor it, but again, we kind of get state-of-the-art results compared to all sorts of competitors. And to our knowledge, again, this is one of the first works that has looked at these two types of shift and how well a model can jointly do across both tasks, out of distribution detection and calibration, as well as still not sacrificing performance on the underlying accuracy of the classification task. So with that, I'm gonna maybe see if there's any questions. I can't see the chat. If there are questions, I can take a few. Otherwise, I can kind of move on to how to actually use out of distribution detection for a real world problem, such as continual learning.
So currently there are no questions in the chat.
Okay.
So we can move on, and I think like we will save the questions at the end of the talk.
Okay, sound great. Okay, so now we have really good methods that are better calibrated, that perform out of distribution detection better by disentangling geometrically a classifier into norms and angles. And so you might ask, why would I care about out of distribution detection? It's often posed as just a binary classification problem. And yes, you can measure AUROC and see how well you're doing it. Why would anyone care about it? And so again, I'll mention this at the end. I think there's a lot of methods that can benefit from this, or problem settings in machine learning, including semi-supervised learning, where you have pseudo labeling. And so uncertainty estimates on your pseudo labels. That is, you have a model trained on labeled data and you make predictions on unlabeled data. Then you can essentially try to ascertain how confident you are on those to determine whether to feed those pseudo labels back into the model. Similarly, continual learning is fundamentally a distribution shift problem. And specifically, what we have in continual learning is, again, rather in the real world, things are not as simple as just train and test. What we'll have is, some deployed model, and then in the real world, you might encounter completely new classes. And this specifically, we're tackling the class incremental continual learning, where you're trying to learn new categories without forgetting old ones, but without necessarily access to those old data or categories. And so again, what we want to do is just adaptive learning, that as it gets new categories of data, it can update the model without forgetting. And that's the key kind of problem: catastrophic forgetting of prior tasks. And again, this is just the vanilla task of continual learning or lifelong learning, and it has several names. And so the key kind of challenge here is that, sure, if you take all your data and all your categories all at once, the model can do well. If we do it sequentially, like it might appear in the real world, then we have this catastrophic forgetting problem where you're overwriting information from past tasks. And of course, there's several different classes of solutions that people have developed here. But the question is, how can we acquire new information without forgetting past tasks? And so there's different classes of solutions to this. There's regularization approaches that try to somehow protect weights or parameters that are important for past tasks. There's learning or growing neural networks where you add new parameters. And there's downsides to both of those. Either they don't deal very well with longer task sequences or require unbounded memory and computation. And so here, what we are actually trying to do is avoid kind of the common method, which is replay. So replay is kind of the third class of methods that is very common these days. And specifically, what you do is you store data from past tasks. This is obviously an approach that's easy to do. You just store past data and replay it when you're learning new tasks. Of course, to infinity, this is just the offline setting. You can just store all your history and then retrain globally on everything. Of course, that's not very efficient. And the people do study how to reduce the amount of replay data. But there's a lot of different concerns for this. This includes not just the memory budget, but actually privacy concerns. If you think about things like hospital data, you might not want to store all your data or any part of the past data. Or if you're transferring models across hospitals, you don't want to, again, have to store data from the other hospital. So there's a lot of privacy concerns. And what we actually have been looking at is something called exemplar-free class incremental learning. That is, we want to do no replay. And there's two classes of doing this. One is we have an ICCV work that's really cool. I'll show a slide for it, but I won't cover it, which just kind of dreams up new data using just a discriminative model or classifier that it learned. Here, I'll be showing a semi-supervised learning kind of setting where we might have access to unlabeled data. And so again, the goal is to learn classification model from incremental stream of data, but we don't want to store either generators, which again have privacy implications. They often memorize the data distributions and you can just back them out to get actual data points, or have to store past data. And so again, this is both to reduce memory as well as address things like privacy concerns. So the approach I'll be talking about that leverages and connects to the outer distribution detection problem that I talked about is semi-supervised continual learning. Here, what we have is a set of unlabeled data in addition to the labeled data. And so the question is, how can we leverage this unlabeled data to reduce catastrophic forgetting? And specifically, this is kind of going along the lines of embodiment. If you have an agent, for example, that's moving around in an environment, it'll always collect a stream of unlabeled data, basically for free, right? As it moves around, it gets a bunch of data for free. Some of it is labeled, but most of it is not labeled. And so there's a question of, or two questions. One is, how do we leverage the stream of unlabeled data? And there's some prior work that have done this, mostly for the web data case where you have very large unlabeled data sets. But really what we're looking at is how to specifically do it for particular types of distributions of data, specifically ones that have correlations. So if you think about an agent moving around in a kitchen or some other type of environment, it'll see correlated sets of objects. That is, in the kitchen, there's a bunch of types of objects that tend to appear together. And so one question that we asked in this work is, does that actually affect some of the prior methods that looked at semi-supervised continual learning? And if so, how can we fix that? And so the formal problem that we set up is what we call realistic semi-supervised learning, continual learning. Here, what we have again is a semi-supervised setting where we have, let's say, 20% labeled data. And this just follows, for example, the parent class structure. And then we have 80% unlabeled data. And we're exploring two types of distribution in the unlabeled data. One is no correlations. That is, the unlabeled data is not correlated. That is, it's not the same types of superclasses as the labeled data. And then the correlation where it is. So you have kind of a correlation between the types of objects that you see. And again, we're trying to mimic the real world. We're using SciFar still to kind of be able to quickly experiment with this setting, but we're trying to mirror what we know exists in the real world. And so the way we do this is actually in a principled kind of methodical way, which is to use SciFar 100. And it actually comes with a superclass structure. That is, all the different categories are separated into buckets of superclasses. For example, you have things like types of animals or flowers and so on, or types of objects. And so out of this, we can have two subsets of data sets. One is where there are no correlations. So the labeled data is, let's say, flowers, and the unlabeled data comes from anywhere, any kind of superclass. And similarly for other tasks. So again, it's a continual learning problem. So we're progressively introduced to these 20 tasks. But we can also have a correlated version of this where the unlabeled data, for example, if the labeled data comes from flowers, then the unlabeled data is also coming from the flowers. Not necessarily, it could be the same classes, but it could also be completely different classes, but just under the same super category. And you might think, why is this an issue? Why would you set this artificial type of thing up? Does it really matter if there are correlations? And we actually show that indeed past methods that worked well under the uncorrelated distribution actually fail under the correlated distribution. And so the intuition that we're going to use to develop our method is to develop several aspects of our method that leverages semi-supervised learning out of distribution detection, which I showed before. So specifically, we can use pseudo-labeling based methods. These are methods, again, that take the labeled data, you learn a model, and then you make predictions on the unlabeled data, and you take the confident ones in order to pick the ones that are hopefully more accurate. And then you use that in some way, and I'll show that in the architecture. And then the key thing that we'll show is that actually all the methods that I showed in the first half out of distribution detection is actually crucial here in order to pick out unlabeled data that's not going to be helpful. We can also use pseudo labeling to do something that's pretty common in continual learning, which is class balance fine tuning. We can also use things like knowledge distillation. And here we can actually use all the unlabeled data. That is, we can make sure that the model that was trained on the past tasks is basically making a certain types of or certain set of predictions on the unlabeled data. And hopefully the new models that we'll learn on the new task will be regularized to be similar to those predictions. And then we can also use some fixed match type methods, if you're familiar with, where we can take the unlabeled data, we can augment it, and just have a consistency loss such that the predictions are consistent across the different augmentations. So this is the overall architecture that we'll have. And again, the key thing is that it's using this outer distribution detection as a selector of which pathways or which loss functions it goes to. And so we have a whole bunch of unlabeled data. And that unlabeled data goes through, of course, feature extraction. And this is through some weak augmentation as well. And then we perform out of distribution detection and determine whether it's in or out of distribution. That is, whether it relates to the old classes or the new classes. And so what we can do is, depending on that, we can feed it to different losses. If it's essentially in distribution, that is, these are confident samples that are in distribution from past tasks, then we can just add it to the cross entropy loss that we use also for the labeled data. Again, we also have some labeled data, a small percentage of it. If it's out of distribution, then we can actually use it for the other two losses, either the distillation loss, which says that our current predictions after training on the current task should be not deviating too much from the past predictions, as well as we could use it across this consistency loss across the weak and strong augmentation. which is basically the fixed match algorithm. What's really cool is based on whether it's in or out of distribution, we can determine whether to use it for soft distillation loss or a hard cross entropy type of loss. And what we show is that these different decisions actually make a difference. And so we can show under our different data sets how well this performs. So this is under the no correlation setting that we talked about. And again, we don't store any past examples, so there is no replay here. And what we show compared to a bunch of continual learning methods that do use replay, that we can actually do really well. The replay-based methods actually have to store up to 750 examples to do as well as we do with no replay examples. And 750, to put it in perspective, is actually quite a lot. It's actually equivalent to about, I think, half the amount of data, or actually three quarters of the amount of labeled data per task that we have. So it's actually a significant amount of storage, as well as, like I mentioned, privacy implications. And so we can do really well with no replay, which is really cool. And one thing I should have mentioned, sorry, the metric that we're using here is forgetting. Again, higher is better, and this is, I don't have the equation here, but it's a forgetting metric that looks at some comparison between the offline upper bound case. But higher is better here and shows less forgetting. And so again, we're competitive with no core set or replay with methods that actually do replay, which is quite significant. And so the takeaway is we don't actually need to store data in this environment that's uncorrelated. In the correlated case, actually, we do have a small amount of replay because this is actually a really difficult case, and we're looking at that. This is a really a good area of future work. These correlations actually do matter, and they actually make everything worse. They actually, interestingly, make a lot of these methods that were labeled or that were developed in order to leverage large unlabeled data sets, they make it much worse. So there's all sorts of distillation-based methods that do well on the uncorrelated set, but actually do quite poorly on the correlated set, even with some replay. Whereas our method is actually doing, again, state of the art. On the other hand, there's a downside. We do use some replay here just because it's so difficult, and that's area of future work. But again, the key is that our method does well across these different distributions, correlated or uncorrelated, compared to prior methods, which only do well under uncorrelated distributions, and we still do better than them. So global distillation, again, is a prior method that was semi-supervised continual learning that has, again, web data for the unlabeled data sets. And then we can show that this method actually scales to larger data sets like tiny ImageNet and so on. That, again, we do really well with a tiny amount of core set. And again, we really want to get rid of that core set. We do have some actual other methods that I won't go into that also does deep dreaming, that is generate data, synthetic data, rather than doing replay. And so we can actually combine this with the semi-supervised case. And here we can show strong results with no core set at all. And it's orthogonal to the semi-supervised setting. And again, we can establish a state-of-the-art with no core set compared to all sorts of other methods with a very relatively small amount of computational overhead. Okay. And so I'm going to wrap up in order to take questions, but the key takeaway that I'd like you to have is one of the key principles that maybe people implicitly discuss in various subdomains of machine learning, but don't explicitly analyze, is distribution shift. And we should really be looking at different types of distribution shift: covariate shift, that is degradations, corruptions, weather, and things like that; prior shift, which could be an imbalance in your label distribution, long-tailed imbalance learning, as well as concept shift, where you have completely new categories. And looking at this in a holistic way and developing methods as we have that can do out of distribution detection and calibration under both or all types of distribution shift, and actually in a manner that we can singulate the effect of each distribution shift on different parts of the neural network, whether it's the feature norms or the angular part, is really, really impactful. And we can really use that to both understand in a more interpretable way what's going on with these models when distribution shift, and also hopefully develop new methods that improve results. So in summary, that's the key thing. Distribution shift is really a unifying concept across many different fields, including calibration, uncertainty estimation, out of distribution detection, robustness, and so on. We've developed several methods that actually do tackle this in a unified way, and we can actually tackle both covariate and semantic shift using a single method and do well both in calibration and out of distribution detection. We have some other works that look at imbalanced learning from a Bayesian perspective as well that I won't cover. And ultimately, what I'd like to do is really, again, unify all these things. And I think there's a lot of interesting, again, applications to both calibration and out of distribution detection under distribution shift, both for continual learning. We have some in submission work on using out of distribution detection to leverage semi-supervised learning, so leveraging unlabeled data in the wild, as well as something called federated learning, where you have many learners that are performing gradient updates, sending it to some central server, which again, you'll have different types of distribution shifts. So we think it's really a unifying concept, and we hope to continue to tackle it in a unified manner. And I'd like to thank all the PhD students, of course, that do all the work, a lot of which have developed the slides that I showed, as well as all the funding sources that showed that provided support for this. And all of the references for this, if you want to look at more details, are on the bottom here. With that, thank you. I'll take questions.
Fantastic. Maybe let's unmute and thank our speaker first, and then we can have we have time for 2 questions. Thank you, Zolf.
Thank you.
Okay, questions? Okay, so I can start with one. The first part of the work, the talk is really fascinating. That's a simple approach of making instant dependent and instant independent decomposition is this powerful in essentially having sensitivity to in and out of distribution. So one thing that I don't have a very good intuition about is why does this instant dependent term, the delta F, become so sensitive to in and out of distribution, right? So you're not training, you don't have any contrastive signal from between in and out distribution. So where does this contrast come from in delta F?
Right, and so I will say we do not have a mechanistic, or analyzing the dynamics of gradient descent and things like that in order to understand what allows it to, or why it actually does learn feature norms that are sensitive to out of distribution data. Obviously, we're kind of showing a lot of empirical evidence that indeed, if we don't have these terms, then it drives the feature norm very high. And so really we came from that intuition, which is just the fact that in order to drive the loss down, it is really just encouraged to drive the feature norms very high, for example, and the angles low. And that if we provide it this flexibility, it's obviously related to just the notion of in deep learning, we want to provide flexibility for the neural network to not cheat or not come up with ways that are suboptimal to drive the loss down. And so we came with that intuition, and then we showed that empirically our intuition is correct. I agree, like an interesting analysis future work would be to try to understand the dynamics of gradient descent and things like that to really understand why it actually does leverage that flexibility. I agree that's a really interesting question. I don't know that I have a satisfying answer besides a lot of intuition, right? Which I'm a strong believer in. If you provide intuition, you should provide some evidence for it. And right now we don't really have evidence for the mechanism, underlying mechanism. Yeah.
Got it. There's a question in the chat from Stefan Larson. Have you looked at or have plans to look at natural language processing tasks?
That's a great question. The answer is yes. We are looking at distribution shift in natural language processing and other, specifically multimodal. We're starting to get really interested, like maybe a lot of other groups in multimodal, combined language and vision, for example. I think one thing is some of these concepts are much more difficult. So for example, out of distribution is much less obvious in language. And I do collaborate with a lot of cool NLP people at Georgia Tech, and we have these discussions all the time. It is often less obvious how to characterize whether something is in or out of distribution detection, just even as you set up the data sets to test it, right? So in computer vision, there's a lot of, we can see the categories, we have some intuition for them, and we can try to measure how in or out of distribution things are and add noise and other things. All of this stuff like adding noise or data augmentation for language is much harder. I agree it's a really interesting open area and one that we are looking at. I don't really have sort of intuitions or answers for at this point. But I think obviously the method we developed is not specific to anything about computer vision. It's really just that in language, you really need to think a lot harder about how to set up these data sets and out of distribution detection and calibration problems or settings themselves. And we are also looking at continual learning as well. So yes, we are looking at it. I don't have any kind of concrete answers or lines of thought of how to tackle them. I think again, what's cool is the methods that we developed are pretty fundamental and principled, so I think they should work under those cases.
So I have one more question,
Sure.
Zolt, if it's okay. It's more of a clarification question for the second part, when the unsupervised data is correlated or uncorrelated, right? So the idea there is that we have a replay buffer, but that replay buffer is not from the previous task. It's just a wide unsupervised set of data points or images that we have access. Now essentially if this set is correlated with the current task, there is going to be large catastrophic forgetting on the previous task. And if it's not correlated necessarily, it's going to be better for catastrophic forgetting, reduce catastrophic forgetting. Is that the message?
I'm not really sure that that's perhaps the case in the sense that, well, so first of all, we don't view it quite as a replay buffer. I guess you can view it that way, but if you have an agent wandering the world, then essentially it's not storing it in memory. It's like it's perceiving it instantaneously across the environment. So of course, there might be a semantics difference there. The other question, I think, again, I agree, like it depends on the unlabeled distribution, whether it has things from past or current tasks. But that's not really what we're looking at. In our case, our unlabeled data had things from both, kind of past and future and current tasks, but were essentially either correlated to the labeled set or not, right? So we're really looking at specifically with respect to that. So is the unlabeled data correlated, not just in the sense that it's exactly the same categories as the past tasks, but under the same super category as the current task, the labeled data. I will have to, I agree with you that there's a separate, it's not orthogonal, but maybe somewhat separate, which is, yes, if you're assuming that there's an unlabeled set, of course, there's a question of if it contains nothing about past tasks, then maybe it won't help anything about the new task, right? All you could see is just it's unlabeled data of the current task, and that's not going to be helpful. But that's not really what we were looking in that work. We were looking at assuming that the unlabeled data is some mixture of things in the world, which could be both past and current tasks. Is it correlated to the labeled data, the current task, or not? Yeah.
Got it.
But I agree, understanding the other aspect would be interesting too. But obviously, to its extremes, if it doesn't have any unlabeled data from past tasks, it's not going to be helpful, probably. Yeah.
Got it. And one last question in the chat, which says, have you tried your models on more complex tasks beyond category classification, which is essentially segmentation task, for example? Have you looked at segmentation?
So we have looked at not segmentation, but object detection. And so we have some in-submission work actually on kind of open set object, semi-supervised object detection, where again, you need to use out-of-distribution detection. And actually, we found that the rankings are the same, where our disentangled method is actually superior to other methods. So, which is cool to see, as in, taking the same method, same disentangled method, apply it to object detection, and show that the scoring function for out-of-distribution detection can actually be used again as part of this like pseudo labeling process that in semi-supervised learning. So we definitely applied it to object detection. Segmentation would be interesting to apply to as well.
Fantastic. Thank you so much. I'm going to pause the recording now and